This is our final lesson in Unit 1415 on data analysis. We are going to cover graphical summaries. We won't talk a lot about that in this lesson. Most of that stuff is more easily handled by working away through some examples, which are given either in the textbook questions or in the learning guide. We're going to focus here on misrepresenting data here. So by the end of this, you want to be familiar with some of the common ways that graphs can be misleading. And we're going to talk a little bit about data in the media. And there you just want to be familiar with some of the common ways that data and statistics can be presented in a misleading way in the media. Now, for the presentation of data and statistics, I think the stuff in the learning guide isn't too bad, so you should take a look at that. I'm going to take a look in this lesson here at some misleading graphs and statistics that have been presented in the media. And we'll see if we can sort of spot the problems in these. So first off, let's just take a look at these two graphs up at the top here. They are showing a graph of, both of them are showing sales over different months, quantity of sales, from July to December. And if you look at these two graphs, graph A seems to suggest that there has been a relatively small increase in sales over the course of those 6 months, whereas graph B shows that there has been an enormous change in sales. Look at the growth in sales over that time. Well, if we look very carefully at these two graphs, we notice that in graph B, they have done this sneaky little thing here where they have omitted a big chunk of their vertical axis. Why have they done that? Well, they have done that in order to make it look like the increase in sales is much more dramatic than it actually is. So we could say something like that the smaller range on the vertical axis makes a small difference appear larger. Small differences So now when we look at the second set of graphs down here, we've got Matthew's test scores. Maybe Matthew's parents have been really on him about how he's been doing in math. So he created these bar graphs to show how he's been doing on his 4 most recent tests. Now, if you were Matthew, which graphs would you show to your parents? And why? Why the one on the right? It does look like you've got bigger test scores because the lines are all higher up. Another reason, maybe? Or any other answers here? Well, what if what Matthew wanted to show was that I've been working really hard and I've really been improving in math? Which graph would he choose to show? He would choose to show the one on the left because it looks like he's really gotten better. Even though all of his marks, when we look at the numbers on the y-axis, are all still in the 60s. This seems to show a lot of improvement. This one makes it look like he's really doing well because all the bars are way up there at the top. So both of these graphs are a little bit misleading for slightly different reasons. A truly accurate graph would probably start at 0, go up to 100 because the tests are probably out of 100 because they're given as percents, and that would give the most accurate reflection of how Matthew is actually doing in math. Maybe Matthew doesn't want to present that information to his parents, so he's choosing a graph depending on kind of the story that he wants to tell. Okay. So how else can they make graphs that are a little bit misleading? Well, we've got 3 graphs here. We'll take a look at the top one first. First off, it's a pictograph. I have no idea why you would want to use a pictograph, but let's say you did. Basically, you use a pictograph probably when you don't want to be very accurate about the kind of data that you're presenting. Now, why is this graph a little bit inaccurate? What can you sort of see in here? Kale, what do you think? Yeah, the fish are massive. The cats and the dogs are small. What does each symbol represent? Well, each symbol represents 10 students. So we've chosen a big fish to represent 10, and we've chosen a tiny little dog to represent 10. So it looks like there are more fish lovers than there are cat and dog lovers, because this sort of bar takes a lot much more space up there. But if we count them up, we've got 10, 20, 30, 40 cat lovers, 40 dog lovers, and only 30 fish lovers. Okay? So this is an example of what the learning guide calls design variation. We've changed the size of the symbols to make something look larger than it actually is. So we could say something like large symbols make the amount appear larger. Appear larger. They've done something a little bit tricky in this one here. Two graphs of computer sales where we're comparing desktops to laptops here. What have they done in graph B to make things a little bit, well, that I as a math teacher am not going to like? How have they tried to make it look like they've sold more desktops in graph B? Daniel. They made it thicker, so it looks like it's got a bigger area here, which probably means more laptops. They didn't even have to do that, because already we've sold twice as many desktops as we have laptops. When we're reading bar graphs, we look at the height. Okay, we don't really care about how wide it is. So I'm not sure why all of our bars should be the same width. So this is just a bad graph all around. But again, they've changed things. They've changed the design of the graph to try to make something look bigger. Okay, question time. So this doesn't appear very well on your photocopy here, but I want you to take a look at this circle graph, okay? This fancy three-dimensional circle graph. And we've got three possibilities here. We want to look at item A, and we want to look at item C. Based on the relative sizes of those two little pie slices, is item A bigger than item C? Is item C bigger than item A? Or are they about the same? What do we think? Cale's shaking his head. What do you think, Cale? You can't tell, but you have to tell. That's the whole point of the graph. You're supposed to look at this graph, and you got to say what you think. So what do you think, Cale? Pick one. It says they're about the same. What do you think, Cheyenne? What? She says whatever. Okay. What do you think? Anybody else? McKenna? A is bigger than C. Anybody else? I'm gonna pick on Abigail here. Abigail says they're about the same. Well, it's always weird when they take a graph. Graphs are supposed to be two-dimensional. We expect them to be two-dimensional, okay, when we draw them. And they make it three-dimensional because it looks kind of nice. What if we take this three-dimensional graph and we turn it into a two-dimensional graph? We see that item A has about 11% of the area. We see that item C down here has 5%. So A should really be about twice as big, a little bit more than twice as big as C is. Why does it look like they're about the same? It's because of that perspective. They put item A's pie slice towards the back, so it's smaller. They put item C's towards the front, so it looks a little bit bigger, and they end up coming out to be about the same. Okay. So anytime you see a graph that's in 3 dimensions, sometimes they do this as bar graphs too, and they make the bars coming out towards you. Be a little bit suspicious. Okay. Our final graph that I think we're going to look at here, selectively omitting data or not putting data in context. So here we've got somebody who has given themselves a headline here, global warming is out of control, because if you look at this over the past 6 months, look at how this graph is, how the average monthly temperature is increasing. It is just skyrocketing up. If this continues, the Earth will be a burning cinder in a few years. What have they? Well, they haven't done anything wrong here. They have actually taken measurements of the average monthly temperature, and they have plotted them accurately. What's wrong here, Alana? Absolutely. So we expect the temperature to increase as we go from January to February to March to April on to July. And then we expect at the end of the year to go back down again. So they're not comparing this over years and years and years. They're just looking at 1 year. They're not placing the data in any kind of context. And they're starting their graph at the coldest possible month and ending it at the warmest possible month so that you can see the maximum sort of trend. Okay. So this happens a lot. You'll see if we were to imagine the graph extending into the previous year, December might be something like a point here, and then it would gradually increase in November and October, and so on like this. And so in the middle of last year, we would have been up at about the same level in the summer. I mean, that doesn't look like global warming is taking off, but if you start the data, if you ignore all this stuff here, sure, it looks like the temperatures are going out of control. Okay. So here's a graph where they have done something extremely tricky. They are plotting the job and health insurance losses. Oh, the title is Job and Health Insurance Losses Accelerating. 14,000 people becoming uninsured every day, and they're plotting the number of uninsured Americans and the unemployment rate. And look at these things, they just perfectly correlate, and they're taking off like that. The weird thing that they have done here is, well, what is the weird thing that they have done? Can anybody, Jake? So they've got March, May, July, September, November, January, March. Yep, so they've picked and choose some of the data in here. November, January, December, I think, July, August, yep. Or are they just alternating every month? Yeah, I think they're just alternating every month there. But that's one way of doing it, is skipping data. The other, Alana. Yeah. So they're plotting two different things. They have two different vertical axes. They have uninsured Americans on this axis over here. So it's being plotted on this axis. And unemployment rate is being plotted on this axis over here. Now notice that neither of these axes start down at 0. This one starts at 4%. This one starts at 44 million. So they're comparing a percent to millions of people. And they've carefully scaled both of their axes so that you can see, well, so that you see exactly what you want to see. Is there some sort of a correlation between the number of uninsured Americans and the unemployment rate? We don't know from looking at this graph. It looks like there is, because that's what they want us to see when they look at it, by careful choosing of the axes. Okay? So this is a rather clever example of a misleading graph. There are more, I don't know, humorous examples of misleading graphs. This is from way back in 2012. What is wrong with this graph? It's almost laughable, isn't it? What's going on here, Liam? How does 60% plus 70% plus 63% add up to be 100%? That's what you're supposed to have in a circle graph. All of your pies are supposed to add up to 100%. It doesn't even look like the slices of the pie are different sizes. I don't know what this graph is supposed to be showing. Okay? So this is good old Fox News. Okay? Oh, this is another one from Fox News. Imagine that. Here they are graphing welfare versus full-time jobs. Okay? And this graph, they've given us a bar graph here. It shows that there are 108.6 million people on welfare and 101.7 million people with a full-time job. So they're making it look like, well, that there are a lot more people on welfare than there are people with a full-time job. This is an example, though, of what the Learning Guide calls using incomparable definitions. Their definition for the people on welfare and their definition of of how they counted the number of people with a full-time job is different. So there's a little of a description here. I'm trying to make it bigger here so you can read it. Their 108 million figure for the number of people on welfare comes from a Census Bureau account. So it's from the census. Of participation in means-tested programs which include anyone residing in a household which one or more person received benefits. So they counted you in this 108 minutes if you lived in a household with a person who was receiving welfare benefits. Okay? This includes individuals who did not themselves receive government benefits. So what kind of bias is this an example of? Not sample bias. This is household bias, where they have taken everybody in a household. If just one person in there receives benefits, they put them all in the benefits category. That's bad enough, but then when they counted the number of people on a full-time job, here we go. On the other hand, people with a full-time job figure included only individuals who worked, not individuals residing in a household where at least one person works. So they used one definition for people on welfare and a different definition for people with a full-time job. And lo and behold, they got more people on welfare than with full-time job because they counted all those people in that person's household as well. Okay. So, I don't mean to pick on Fox News, but it's just so easy to pick on Fox News. Can you see this graph particularly well? No. Well, it's showing the unemployment rate under President Obama. 9%, 8.9%, 8.8%, 9%, 9.1, 9.2, 9.1, 9.1, 9.1, 9, 8.6. 8.6. But it's plotted on the same level as 9.0. Now, why do you think they did that? To make it look like he hasn't done a good job, that the unemployment rate has stayed basically the same. If you took this data point and you plotted it where it's supposed to go, well, it should be way down. It should be way down here, below the 8.8%. Okay? So if you were to actually do the graph the way you're supposed to, this one doesn't show up particularly well either, what you would see is that our unemployment rate kind of goes down and then it goes up, and then it suddenly goes back down as it drops from 9 to 8.6%. I don't know, I guess Fox News didn't like that. So they basically deliberately misinterpreted the data. There's no excuse for that. That doesn't even, I shouldn't even have to mention that in a math course. So always when you're looking at a graph, consider the bias or possible biases of the source of that data. Okay? And that's where we're going to stop.